My name is Kurt Roth. I work for the Fraunhofer USA Center for Manufacturing Innovation, leading energy systems applied R&D there. We're a nonprofit applied R&D organization that operates globally. But we do a good amount of work in energy systems in the team I work with. And really want to just build on what Tony was talking about in terms of to help tee up some of the discussions and some of the presentations, getting more into the topic of heat pumps and some of the particular challenges and opportunities. And so one of these theses that's been floating, that's really been around a lot of what we've been talking about as a team on this project is how can we really leverage all the things that have been done with buildings related to heat pump R&D and technology development. This has been going on for decades. There's been a lot of progress in terms of improving efficiency, particularly improving capacity for lower temperatures, so for higher lift kind of applications. And how can that be leveraged? But I think it's really important to kind of point out, again, some of the things that Tony touched on. What are the challenges? What is different when you try to go to these higher temperature applications instead of where you have, you're pumping heat from, say, something on the order of 0 degrees Celsius up to something around 30 or 40, something like that. But if you're going to do something where you're trying to operate at temperatures which are appreciably higher than that, well, as you have different refrigerants that probably make sense. The properties are different in terms of how efficient the cycles can operate. And also in a lot of cases, the pressures get out of control. You see some of the critical temperatures here, and also you see some of the pressures under those conditions. And you're getting onto order of, tens, if not over hundreds, on the order of 100 atmosphere, particularly if you're using something like CO2, or you can see ammonia also goes to very high pressures. This makes you potentially think about how you design your compressors, doing that differently. There are things around, do you have a different kind of, if you're using a vapor compression cycle, do you do something different in terms of lubricants, say, for those cycles? You may need larger IR side heat exchangers than you typically use in a conventional system now, where you have say a natural gas fired kind of space heating heating for these kind of processes, where you can get a lot more heat transfer through because you have a larger temperature difference between the combustion gases and where you're transferring heat to. You're trying to minimize the amount of lift on the cycle, so you're going to be operating with smaller delta T's, and so that might change the whole how you interface with the process as well. And overall, there's been a real challenge because the low-cost natural gas, particularly in the United States, has really made very little economic incentive for people to pursue heat pumps in these applications on top of all the technical challenges. And so this is really, how do we work with these kind of things? Now, in some places there has been some progress. This is an example of a heat pump, which is from Japan. It's supercritical CO2 industrial heat pump, and it can achieve reasonable kinds of performance levels. It's also producing, it's doing some water cooling as well as providing heat around 120 degrees C. Somewhat limited capacity, but around 300K BTUs an hour. But you could actually gang these up to do multiple to provide multiple sources of heat for an application. You can see they're really targeting some of these mainstream applications, which we're looking at in the low temperature world. So this is very, this is interesting. But again, Japan's been a place where there really hasn't been the natural gas. They've been importing LNG for process heat in other cases. So it makes sense that there would have been more development of these kinds of technologies there. The question is, how can we go even higher? How can we make this even more effective in a wider range of applications for industrial heat pumps? And so if we look at opportunities, clearly refrigerants are a major need, as the IEA has looked at, and also Tony's identified, and looking at alternative cycles, non-vapor compression cycles, and ways to upgrade waste heat. That's something which seems to be very important, and builds on the whole idea of doing pinch point kind of analyses of these cycles to potentially even re-engineer processes to work at somewhat lower temperatures, or to design them to work with heat pumps more effectively. And finally, there are a variety of tricks that people have played to make vapor compression cycles more efficient in buildings applications. These range from cascading systems where you have multiple refrigerants that are used to get higher lifts, things like refrigerant economizer, and also multiple stages of compression, which can again allow you to get higher performance when you have higher lift. So these are some of the opportunities, but really what we are looking for today is to get your input on what are the opportunities that are most promising and what should the research priorities be, and really look forward to hearing what the speakers' perspectives are on this, and then a lively discussion about how we should move ahead to realize this large decarbonization opportunity.